Hello, good afternoon, everyone. My name is Chengzhi. I am from Karlsruhe Institute of Technology. The topic of the presentation I am going to give today is Object Detection in 3D Point Clouds via Local Correlation-Aware Point Embedding. Here are the contents of my presentation. Firstly, I will give a bit background knowledge on deep learning on 3D data. Then I will give a brief review on some related work, including PointNet and Frustum PointNet. Next, I will present our proposed method, including the local correlation-aware point embedding blocks. Finally, the experimental results will be given, as well as the conclusions. In real world, there are various 3D data formats. For example, multi-view images, volumetric data, octree data, or polygonal meshes and point clouds. Those 3D data may be mainly categorized into two subsets. The first one is rasterized form with regular grids, including images and voxel-based volumetric data. The second one is geometric forms, including point clouds and meshes. They are usually in irregular forms. For the rasterized forms, it is quite easy to extend 2D convolutional neural networks to those 3D convolutional neural networks, since those are just regular grids and can directly apply those convolutional operations. However, when it comes to those irregular forms, it is quite hard to directly apply deep learning methods on them, since normally defined 2D convolution operations do not fit anymore. The first proposed method that applies deep learning techniques on point cloud data is PointNet. It used lots of fully connected layers to get the global information of the input point cloud, but they did not define any convolutional-like operations and no local information was used. Their subsequent work, PointNet++, used a multi-scale grouping strategy to get the local information. But in the end, it is just applying PointNet on different scales. Still, no 3D convolution operations were defined. Here, we generalized the idea of edge-conv to capture local geometric structure of point clouds. K-nearest neighbors of each point are selected to contribute in computing its local features, processing the input features through one fully connected layer followed by one plane layer. Finally, we get the embedded output features of points in which the local correlation information are implicitly represented. N stands for the number of points, K stands for the number of neighbor points selected, C in, C out stands for the channel numbers of input features and embedded output features, respectively. With these local correlation-aware point embedding blocks, the representation of each point will change from 3D coordinates into embedded vector. And going deeper through our network, each point will be further embedded. Points that have similar features may be grouped together as neighbors in the later net layers. The task we are looking into here is 3D object detection. Our research dataset is Kitty, an open point cloud dataset created with LiDAR sensors. We use the Frustum PointNet as our backbone structure. Its basic idea is to project pre-computed 2D bounding boxes onto the point cloud to get the frustums for all objects. Then, for each frustum, do a binary segmentation to extract the points that belong to this object. Based on the method of Frustum PointNet, this is our new pipeline. Some parts of it are identical to the Frustum PointNet as colorized in blue, except for the segmentation part as colorized in orange. We also have added an additional local feature embedding block for a head, as colorized in green. The fully connected operations in the original 3D instance segmentation network may also be replaced by the proposed local feature-based embedding operations. These are the detailed network structures of our proposed local feature-based embedding block and the segmentation network. The local feature-based embedding block consists of a spatial invariant transform net and a sequence of k-nearest neighbor point embedding subblocks. Note that, different from edge-conv, we still consider some original features of points, even in the later layers. In our case, the intensities of points are concatenated to them at the beginning of each point neighborhood embedding subblock, because we think some features of points, like intensities, should not be compared directly the same as the point coordinates. For the segmentation network, using PointNet as a backbone, we replaced the fully connected layers with our forehead-defined local feature embedding layers. Inspired by ResNet, we used some skip links trying to make good use of features at different layers. Additional features obtained from the spatial transform net are also concatenated before the last 3 layers. Here, we give a more detailed explanation about what are the input and output of each subblock. For the current best setting, we definitely apply the invariance transform net. For each point, we use its self-feature and the difference between this point and its neighbors as neighborhood paired features. Note that the Euclidean distance between 2 points may also be considered. At the same time, some original features of points could also be concatenated at appropriate positions in each embedding block. For each point, we select 4 neighbor points to compute the local feature. We choose 64 as the number of output feature channels of each local feature embedding subblock. Here are some experimental results. This is the 3D object detection average precision on the Kitty test set. As you can see from the table, comparing to our baseline Frustum PointNet, we got about 1.8% boost on precision of detection for car moderate. We have also tested the influence of different subblocks. As you can see from the table, each subblock contributes a bit to the performance improvement. Here are some visualized results from spatial invariance transform subblock. Those red point clouds are the frustums processed before the spatial transform net, and the blue points are the frustums processed after the spatial transform net. We can clearly observe that frustums have been slightly rotated to similar orientations. That is, left frustums rotated slightly to the right, while right ones rotate slightly to the left. Here are some more visualized results with our improved method. For example, in this case, false positive has been corrected. In this scenario, false negative has been corrected. In this scenario, the 3D bounding box of the car has been improved. To conclude, based on our baseline of Frustum PointNet, in order to improve 3D detection precision, we used a local correlation-aware point embedding method. We added a new local feature-based embedding block, as well as a spatial invariance transform net. We have also modified the segmentation network to further improve the detection precision. Regarding possible feature directions, we can try to find other possible pre-processing operations for the better normalization of input frustums. We can also try to take the non-Euclideanness of point cloud data into consideration when computing its local features, as well as design more flexible and interpretable network architectures. Thanks a lot for your attention.